Hello. This presentation will start the mathematical part of the course. We'll be talking about linear and affine transformations. For simplicity, we'll start working with R2, but mostly we're interested in R3 because we're talking about 3D computer graphics. I want to mention first how they fit into the graphics pipeline, how transformations are used, and then we'll get into the mathematical constructions. So, and this is taken from the first part of Chapter 2 in the book, which is available online as a PDF file. So the graphics pipeline, in its simplest form, has a series of transformations that are applied to points or objects to place them in 3 space and then place them on the screen for viewing in the image. So we start off with some points, which I'll call x. X denotes a point in R2 or R3, and this is in so-called local coordinates. And the first step here typically is to transform this by a model matrix M, and we form mx, this is m times x, in world coordinates. And this is done with a model matrix M that transforms the point x. And this usually, we have a world coordinates means we've got x, y, z space where our 3D objects are living, and we've placed the object in world coordinates. Now, we want to view this object from some particular point of view, so we transform it again. We apply another matrix V mx to mx, which of course is the same as Vmx, and this gives the points in so-called view coordinates. So here we're thinking of the viewer is specified by a matrix V, and we're either thinking of moving the viewer around in space to look at objects, or of moving the objects around in space to sit in front of the viewer. And finally, there's a projection matrix, P, and this places we form PVMX, and this gives us the points in screen coordinates. So once it's in screen coordinates, this gives the position of the points on this image that we're looking at. It takes into account things like perspective, that things look smaller if they're further away, and so forth. And then there's a final step here that's typically put in that I won't explain yet, which is the so-called perspective division. This we'll learn about in subsequent lectures, but this is the final step to do the full transformation into screen coordinates. And typically these matrices M, V, and P are operating on points in 3 space, but they're actually going to be 4x4 matrices, as we'll see in future lectures when we get to that topic. So maybe to give an example of this, suppose we're modeling a Ferris wheel. So I've got a Ferris wheel, like you might see at a fair, and it's got a chair on it. And an artist is designing a chair. So the artist would build a chair in local coordinates. Maybe build a chair, I don't know if I can draw a chair very well. Build a chair maybe centered at the origin. And that would be, each point on the chair would be some point x, right? So x might be this corner of the chair here. And then you'd form mx to move the chair to the appropriate position on the Ferris wheel. If the Ferris wheel is turning, the position might depend on time and so forth. So m would depend on time, and we'd move the point to world coordinates in the right place. And now we hit that with the viewer. Vmx gives the position of the Ferris wheel relative to the viewer and describes where the point on the chair is relative to the viewer. And then finally, PVMX would map the point to some pixel on the screen where we're rendering the image, and then the chair would be rendered at the correct place. in the screen. Okay, so let me switch and talk about linear transformations. So I'm going to talk about linear transformations in R2, or 2 space. Typically, we'll want to really work in R3, but the mathematical theory is almost identical for R2 and R3, and it's a lot easier just to visualize and draw things on the board in R2. So I'll start working in R2, and later on we'll talk about how to transform this all to R3. So points in R2, they're given by xy coordinates. So I'm going to denote a point as a x with a vector sign over it like that. In the textbook, it's denoted as a boldface x. I don't use the vector sign notation in the book, I use a boldface x. And what this means in R2 is that it's a pair of points. x1, x2. x1 is the so-called x coordinate, x2 is the y coordinate. We might also write it as xy, that's a different x, not boldface. X and y here are now scalars. This is the x component of a point and the y component of the point. And these are really viewed as column vectors. So strictly speaking, this means the column vector x1, x2, and this means the column vector xy. So points are column vectors. Or in R2, 2x1 matrices. Okay. And then, of course, R2 is just the set of all pairs xy, where x and y are scalars. Right. So that's 2 space. So a transformation, also called a mapping or function, a transformation is a mapping or function. All those words really mean the same thing. I'll use either capital A, capital B, and so on as names for transformations, or function names like f and g and so on. It's a mapping sending points in R2 to points in R2. So it's just moving points around in the plane. And then the transformation A is linear if the following 2 things hold. So one is A of alpha times x equals alpha of A times x. For all scalars alpha, for all alpha in the real numbers, and all x points in R2. And also, if A of x plus y equals A of x plus A of y, for all points x and y in R2. So this is a linear transformation. This is just the same thing as the usual linear transformations like you learned about in linear algebra. There's nothing very new here. So as a theorem, for instance, here, very simple one, if A is linear, then A of the 0 vector is equal to the 0 vector, where here's some new notation. 0 vector is the origin, the vector 0, 0. The proof is very simple here. And for any x, we have that A of 0 vector is equal to A of 0 times x is equal to 0 times A of x is equal to the 0 vector. So linear transformations take the origin to the origin. So for examples of linear transformations, so the first one is, let's let A map a tuple xy, the point xy, to the point minus y x. So it's easy to check, go back to the conditions for linear, that this is a linear transformation. We can also take a look at what this does. Let me draw the x-axis and the y-axis on the plane. And I've got some point here with coordinates x and y. And it gets mapped to the point with coordinates negative y and x. So y is this height here. So on the x-axis, here's negative y, x, and x has this length, so here's height x. So this point here gets mapped by A to that point there. In fact, it's not hard to see that what's happened here is that we have a right angle. And so in fact, this mapping, it's not hard to check. This is a rotation of 90 degrees, or pi halves radians, counterclockwise. CCW means counterclockwise around the origin. So here we have a very simple linear transformation. It's just a rotation. We will also denote this as r 90 degrees or r pi halves, depending on whether we're working with angles or radians, is the name of this transformation. Okay, so that was the first example. The second example is with something like this. A of the pair xy is equal to x plus y, comma y. So we'll see in the next lecture this is a shearing transformation. I'm not going to draw too much for it right now, but you can easily check that it's linear. This is also linear. So another example is the identity transformation. Which I'll use the name I for. In this case, it's mapping every point x to itself. So it's just the identity map. It sends every point to itself. It doesn't. The transformation that doesn't move anything at all is clearly linear. And then also the zero transformation, which maps everything to zero. It would be just A of x equals 0 for all x. And R2. Okay, good. So now next we're going to try some examples of things that are not linear. So before I define affine transformation, I want to define the notion of a translation. A translation is a mapping which moves points around without changing their size or their shape or their orientation. It only changes their position. So the definition is then a translation is a transformation A mapping R2 to R2 such that A satisfies the following properties. A of x is equal to x plus u for some fixed point or displacement u in R2. So this is called, in fact, T sub u. T sub u denotes the translation by the amount u. So T sub u of x equals x plus u. So the first thing to notice here, so the first remark is that for u equal the 0 vector, T sub u is just the identity. X plus 0 is just the identity. T sub u is T sub 0 is the identity. It doesn't change the point at all. On the other hand, for u not equal to 0, T sub u is not linear. And one way to see this is that it doesn't map the origin to the origin, since, for instance, T sub u of 0 is equal to 0 plus u, which equals u, and that's not equal to 0, but a linear map would always map 0 to 0. So it's not linear, and this is a special case of what's known as an affine transformation. So I can define that now. An affine transformation A is a transformation of the form A of x equals b of x plus u, where B is a linear transformation, a fixed linear transformation, and U is a fixed point in R2. So clearly, a translation is a special case of an affine transformation. So translations are affine transformations, and also every linear transformation is an affine transformation. Because you can just take u equal to 0. So as one final definition, let's talk about the composition of two mappings. This is the usual definition of composition of functions. If A and B are transformations, then their composition written A little circle B, A composed with B, is defined by A composed with B when applied to X is equal to A of B of X. So we just, when we compute A composed with B of X, we first compute B of X. That gives us another point in R2, and then we take A of that. So when we're thinking about how these A and B are being applied, A composed with B first applies B, and then applies A. So even though A is written first, B gets applied first, and then A gets applied to move the point around. So in particular, an affine transformation has the form T sub u composed with B, where B is a linear transformation, and of course u is a point in R2. And this is because T sub u composed with B applied to X is equal to T sub u of B of X, and that's equal to B of X plus u, which is the form that we had for affine transformations in the definition on the previous image, on the previous board. Okay, so this lecture will stop here. The next one will take up techniques for visualizing the effects of transformations in R2. Thank you.